Cosmologists have long been interested in Proxima Centauri, the star closest to our planetary group. This small red dwarf, which was discovered in 1915 by Scottish space expert Robert Inennes, is crucial to the Alpha Centauri framework, which also includes Alpha Centauri A and B. Despite being only 4.24 light-years away, Proxima Centauri is invisible to the naked eye due to its relatively low brilliance. In any case, Proxima Centauri is highly esteemed in science, especially as the host star of Proxima B, an exoplanet that orbits within the star's habitable zone. Red dwarfs like Proxima Centauri are smaller, cooler, and much longer-lived than stars like our Sun. They are difficult to observe due to their low glow, but this also suggests that their habitable zones are much closer to the star. For Proxima Centauri, this means an orbital distance of only 0.005 astronomical units, which is a small fraction of the distance between Earth and the Sun. Because of this proximity, Proxima B is subject to significant stellar activity, such as frequent solar flares and high radiation levels, which creates an atmosphere that is very different from Earth's. The discovery of Proxima B was a remarkable feat in exoplanet research. Using the radial velocity method, astronomers detected faint oscillations in Proxima Centauri's position caused by an orbiting planet's gravitational pull. These oscillations enabled researchers to determine the planet's mass and orbital period. In 2016, the European Southern Observatory formally confirmed Proxima B's existence, signaling a breakthrough in the hunt for potentially habitable worlds outside of our planetary system. However, ground-based observations have yielded important information about Proxima B, but with significant limitations. More sophisticated observational tools like the James Webb Space Telescope, JWST, are essential for revealing more details about Proxima's environment and its potential for life because atmospheric distortion and light interference make it impossible for Earth-based telescopes to gather detailed information about the planet's surface or atmosphere. The majority of the data we have, such as its mass, distance from the star, and orbital characteristics, depends on indirect measurements. Close to it is impossible to overstate Centauri's significance as a gateway to understanding exoplanetary systems because, as the nearest star system to Earth, it provides a rare opportunity to investigate the conditions required for life. Proxima B, in particular, offers an alluring prospect of a rocky planet the size of Earth that may contain water and possibly life, but the difficulties presented by its hostile climate make it a difficult puzzle for researchers to solve. The James Webb Space Telescope. While Hubble has offered important insights into the universe, JWST is a revolutionary instrument meant to replace the Hubble Space Telescope. It was created to push the limits of human knowledge and address the shortcomings of its predecessor, but its capabilities are constrained by its emphasis on visible and ultraviolet light. On the other hand, JWST is designed to study the cosmos using infrared wavelengths, enabling it to see through massive dust clouds and find things that Hubble cannot see. One of the main components of JWST is its primary mirror, which is an amazing 6.5 m in diameter and twice as large as Hubble's mirror. This larger mirror allows JWST to collect a lot more light, which increases its infrared reflectivity and allows it to observe extremely faint and far-off objects coated in a thin layer of gold. The mirror's 18 hexagonal parts combine to provide an extremely sensitive viewing platform. The JWST sunshield, which maintains the telescope's equipment at a consistent temperature of around -233 degrees Celsius, is another groundbreaking invention. Unlike Hubble, which orbits Earth, JWST operates from the second Lagrange point L2, a stable position approximately 1.5 million kilometers from our planet. This location minimizes interference from Earth's heat and light, allowing JWST to maintain continuous observations. This extremely cold environment is essential for detecting faint infrared signals without interference from the telescope's own heat. From the first galaxies to the atmospheres of exoplanets like Proxima B, the telescope can study it all. Its capacity to detect infrared light is particularly significant because it enables astronomers to concentrate on redshifted phenomena, objects whose light has been stretched to longer wavelengths as the universe expands. JWST's capabilities go far beyond simple observation. With its cutting-edge instruments, such as the near-infrared camera and IR cam, the mid-infrared instrument MIRI, and the near-infrared spectrograph, it is intended to provide answers to some of the most fundamental questions in science, such as the formation of stars, the origins of galaxies, and the conditions that could support life on other planets. NR specifications JWST is more than simply a telescope. It's a laboratory, a time machine, and an example of human ingenuity. Proxima B has fascinated both scientists and the general public as a possible second Earth because it is located within its star's habitable zone and has the conditions to possibly support liquid water, a necessary component for life as we know it. With a mass about 1.17 times that of Earth, Proxima B is probably a rocky planet with a composition similar to our own, making it an ideal target for research into the possibility of life beyond our solar system. However, Proxima B is far from an ideal twin of Earth. One of its most remarkable features is that it is tidally locked, meaning that one side of the planet is in perpetual sunlight while the other is in perpetual darkness. This creates a unique environment with extreme temperature differences between the two hemispheres. Proxima B's host star, Proxima Centauri, is a red dwarf known for its intense solar flares that can emit bursts of X-rays and ultraviolet radiation. These flares could gradually remove the planet's atmosphere, exposing its surface to the harshness of space. If Proxima B retains any atmosphere, it would likely require a strong magnetic field to protect it from radiation. Without such protection, the surface and atmosphere would be hostile to life as we know it. The terminator line, the area where day meets night, may offer a narrow, peculiar zone with conditions mild enough to support life. Scientists are still optimistic about the possibility of life on Proxima B despite these obstacles because the planet's placement within the habitable zone implies that liquid water may exist on its surface or in subsurface reservoirs. Life may adapt to the harsh conditions, similar to Earth's extraterrestrials, which are organisms that flourish in harsh environments like deep-sea hydrothermal vents or high radiation zones. These adaptations could include radiation-resistant subsurface habitats or special biochemical processes. Proxima B offers an alluring possibility of a rocky Earth-like world that could harbor the conditions necessary for life. As our technology advances, so does our ability to explore this fascinating planet and uncover its secrets. The search for life on Proxima B is more than just a scientific endeavor. It is a quest to answer one of humanity's oldest questions. Are we alone in the universe? Its environment is greatly impacted by the characteristics of its host star, Proxima Centauri, which is a red dwarf smaller, cooler, and much less luminous than our Sun. Because of its smaller size and lower temperature, its habitable zone is much closer, drawing Proxima B into an orbit that is only 0.05 astronomical units from the star, or roughly 4 times closer than Earth is to the Sun. One major problem is Proxima Centauri's intense and frequent solar flares, which are sudden, powerful energy bursts that release high doses of X-rays and ultraviolet radiation. These flares are much more common and vigorous in red dwarfs than in stars like our Sun, and for Proxima B, this means a constant barrage of high-energy particles that could gradually remove the planet's atmosphere without a protective magnetic field. Even if Proxima B preserves some of its atmosphere, any atmosphere there would be susceptible to erosion, exposing its surface to harsh radiation. Proxima Centauri's radiation poses significant challenges for life because high UV radiation levels can break molecular bonds, preventing the formation of complex organic compounds. This would significantly limit the potential for life to develop or sustain itself on the planet's surface. On Earth, organisms like Deinonychus radiourans have evolved mechanisms to repair radiation-induced DNA damage, suggesting that life on Proxima B could similarly adapt, but the level of radiation resistance needed would be extremely high, possibly requiring completely new biochemistries. Interestingly, while one half of the world is always exposed to radiation from Proxima Centauri, the neatly locked nature of Proxima B may provide some protection, and the planet's dark side may serve as a haven. In addition, if Proxima B has subsurface oceans, they could offer a stable, radiation-free environment where microbial life might flourish, similar to the ecosystems surrounding hydrothermal vents on Earth. Despite these obstacles, Scientists are hopeful that Proxima B's unique environment offers a valuable opportunity to study the resilience of life by understanding how organisms might survive or even thrive under such conditions. Surface regions or deep caverns could protect potential life forms from the worst of the radiation. Scientists can learn more about what constitutes a livable planet. Proxima is a cosmic laboratory for determining the boundaries of life itself, not merely a possible home for life. The planet is a prime prospect for more research using modern telescopes and technologies because of its closeness to Earth and placement inside its star's habitable zone. Researchers will keep an eye out for indications of life and habitability at Proxima B. Although it is yet unknown whether Proxima B can sustain life in the conventional sense, its finding represents a significant advancement in the effort to address one of humanity's most pressing issues. The discovery of Proxima B and its possible habitability is only one piece of the larger puzzle of exoplanet research. Further steps in this field include not only improving our knowledge of planets like Proxima B but also extending the search to other star systems. Are we alone in the universe? There are now thousands of exoplanets known to exist, many of which are found near the habitable regions of their parent stars. It is anticipated that the James Webb Space Telescope, JWST, will completely transform our capacity to examine these planets, especially their atmospheres, in previously unheard-of detail. JWST's spectroscopic instruments can identify molecules like carbon dioxide, methane, and water vapor in an exoplanet's atmosphere. Important markers of biological activity or possible habitability. Scientists can find signs of life or at least establish the conditions for its possibility by examining the atmospheric makeup of exoplanets, particularly those in their star's habitable zones. Meanwhile, Proxima B has attracted a lot of attention because of its proximity and encouraging circumstances. Other exoplanets that circle stars like our Sun, including those in the Alpha Centauri system, or those found by satellites like the TESS Transiting Exoplanet Survey spacecraft, are also excellent possibilities for further investigation. The cosmos is full with possible planets where life may arise, whether they are inside the habitable zones of bigger stars or red dwarfs, and this becomes more evident the more we learn. Deciphering the intricate interactions between elements that contribute to a planet's suitability for life is the main task, and this pursuit is being further accelerated by the expanding technical developments in space travel. Future space missions, including those aimed at studying exoplanetary atmospheres and planetary surfaces more directly, may take inspiration from current endeavors like the successful landing of rovers on Mars and the upcoming missions to ice moons in our own solar system. These missions will not only help us understand the Earth-like environments beyond our solar system but also provide insights into the broader question of life's resilience in extreme environments, ultimately the search for life beyond Earth and the study of planets like Proxima B hold profound implications for humanity's place in the cosmos. While Proxima B may not be the next Earth, its discovery highlights that habitable worlds are not confined to our home planet. It also underscores the importance of continued exploration and technological innovation to answer some of the most fundamental questions about life, the universe, and everything in between. As we expand our reach into the cosmos, the coming decades promise exciting discoveries and potential breakthroughs. Whether we discover additional Earth-like planets around the galaxy or detect microbial life on Proxima B, every discovery will influence how we see the cosmos and our role in it. Once confined to science fiction, the study of far-off stars and their planets is quickly emerging as one of humanity's most exciting and motivating scientific endeavors.